Talk by Alex Shtoff from Yahoo Research will be on low-rank field-weighted factorization machines for low latency item recommendation. Please, Alex. Can you reset the timer?
Well, yes. Okay. So, hello, I'm Alex. I actually don't work for Yahoo anymore, but this research was done when I did. So, let's begin. So, this is our agenda. We'll first describe a short overview of factorization machines.
Could you please speak closer to the mic?
Yes, describe a short overview of factorization machines and their variants. Then we will describe the problem of inefficiency of one of these variants. Then our solution and some results. And the business I come from is an online advertising team. So the setup is that there is a large catalog of items, like tens of thousands or more. And we need extremely high throughput and extremely low latency, like ranking a huge catalog in a few milliseconds and do it a few billion times per day. And factorization machines are one of the model families that actually can achieve it because they provide a good balance between their accuracy or their expressive power and their speed. So when training factorization machines, typically we use tabular data. And in this work, we divide the table into fields that represent context or users and fields that represent items. Fields are essentially the columns of the table. That's the terminology. So in this example, we have age and country as the context fields and item type and the last time a user saw this item, for example, as the item fields. Now, this last seen field appears numerical because, well, it's maybe the number of seconds, but typically numerical fields in factorization machines are quantized and they become categorical. So we are given a table of categorical fields. A typical encoding is one hot encoding of all of the fields. And here is the factorization machine model. It was proposed by Stephen Randall in 2010. It's not something new. And what it does, it combines a linear model with pairwise interactions of all the features. The pairwise interactions are essentially a quadratic function of x, of the features, and the coefficients of these quadratic functions are factorized in the form of low-dimensional vectors. So conceptually, since everything is one hot encoding, it's equivalent to just pulling out the embedding vectors of the relevant features. So in this example, the user is of a certain age, they came from a certain country, the item is of a specific type, and the last seen time is something happened here. Okay, I don't know what. Yes, and the last seen time fell into a certain bin. And then these vectors are, we compute the pairwise inner products of all vectors with each other and obtain the result. So in this case, we have 4 fields, 12 features, because we have 12 rows in the table, and the embedding dimension, we call it k. Now, an interesting property of factorization machines, and this is one of the things that makes them so efficient, is that despite the fact that the formula originally is written in terms of all pairs of interactions, it can be essentially reformulated as an equivalent formula that can be computed in linear time. So here we see that we just compute the squared norm of the vectors and subtract the square norms of individual vectors multiplied by their corresponding feature indicators. Now, during ranking, it's even more interesting because when we rank many items for a given user in a given context, it's the same user and the same context for all items. So essentially, the context fields are replicated. And with factorization machines, we can rewrite this simpler linear time formula as a formula with a sum over the context vectors and a sum over item vectors of both of the parts of both sums. And in this case, we achieve a ranking time or scoring time that is proportional to the number of context fields only once per query And for each item, we pay only computational time that's in proportional to the number of item fields. So it means that practically, if I want to take a model, and I just discovered 2 new context fields or 10 new context fields I want to add to my model, they're practically free at inference time. I don't need to think about how will it affect my latency, the latency of my system. So beyond the factorization machines that were proposed by Stephen Randall, there are many variants in the literature, so-called field-informed variants. And we saw that with factorization machines, we compute interactions between all pairs of features. But maybe age vectors interact with country vectors in a different manner than age vectors interact with, for example, item type vectors. So in this sense, we'd like to incorporate the field information, the color of the rows in the table, into the model. And there are many variants that do it, and in this work, we'll concentrate only on one of these variants. That's the field-weighted factorization machine. And its formula looks like this. It appears familiar or very similar to the factorization machines. We have pairwise interactions of all pairs of features, but we also have a matrix R that encodes the strength of interactions between fields, right? So we have R age country, we have R age item type, and so on. But when we want to do efficient inference, we don't have a magic formula that transforms it to something that can be computed in linear time. And suppose that the number of fields is large, like for example 100 fields, this becomes very prohibitive in real-time systems. So there is a very simple heuristic. It's pruning. It's well known in machine learning, not only in factorization machines. We take this matrix R and we keep only like, I don't know, 5 or 10% of the most strong interactions, right? And zero out the rest. So pruning has several drawbacks. So first, we lose accuracy because, well, we modify the model. The model was optimized and trained to minimize some loss. It no longer minimizes that loss. And the second one is that the trained model is not identical to the model that is deployed in production and does the ranking. And when the system needs to monitor a model, validate it, make sure that it works as intended, this becomes complex. And of course, the addition of new context fields is no longer free. We need to think about the latency effect of each new context field. So in this work, we propose an alternative to pruning for field-weighted factorization machines. And this alternative achieves something similar to what factorization machines can provide. So we pay only once per query for context fields. We pay for each item time that is proportional to the number of item fields. We pay an additional price that we call it rho. It's a factor. So for factorization machines, rho is equal to 1, but for our models, it can be larger. And we show in the paper that we achieve a better speed and accuracy trade-off than pruning. So let's describe our solution. So first, to describe it, well, we don't need this complication of RFIFJ because everything is one-hot encoded. So there is one vector for each field. Let's call them V1 up to V4 in this example because we have 4 fields. And well, this sum of inner products becomes simpler. And for convenience, instead of making sure that we multiply all pairs of features only once, we allow to multiply them twice, right? So we have VI Vj and Vj Vi. That's why we have this 1/2 factor there. But for that to be equivalent, we need R to be a symmetric matrix. And we need it to have a 0 diagonal, so we don't have an interaction of Vi with itself. So that's our assumption. R is a symmetric and hollow matrix. And to describe our solution, we go a little bit back and look at the original factorization machines that were described by Stephen Randall. So Randall has this inner product of all vectors, and it's equivalent to a field-weighted variant when all the weights are 1. And is this a field interaction matrix? It's all ones and zeros in the diagonal. And what makes factorization machines fast is this special structure of this field interaction matrix. It can be written as a diagonal plus low rank. So you can see the low rank part. It's the one column multiplied by one row of ones, plus a diagonal part of -1s. And it appears that diagonal plus low rank matrices in general can provide very efficient inference. And this is the lemma we have from the paper. So we have some symmetric matrix R, and we have its diagonal plus low rank factorization. It resembles a little bit the spectral factorization of symmetric matrices, and not a coincidence. And now we define a matrix P. It's a product of this U from the factorization, and V are simply the embedding vectors, the H vector, the gender vector, and so on. And we have a linear time formula for computing all pairs inner products if someone gave us this field interaction matrix in a factorized form. So where's the magic? Well, there is no magic. We essentially pay when we compute the matrix product. But if the matrix U has low rank, like a rank of row in this case, we don't pay a lot. It's very fast. And of course, I promised you separation of context fields and item fields. So we can take the matrix U from the diagonal plus low rank factorization and divide it into context columns and item columns. Similarly, we can take our embedding vectors and divide them into item vectors and context vectors, like we did in the beginning. And in this case, we can write P as a sum of two products. And the first part is the context part. It can be computed only once per query. So again, we are paying only at inference, only time this is proportional to the number of context fields. So that's the result. So here's our idea, right? Instead of learning the matrix R, we learn its decomposition. We learn U, the diagonal, and we learn the diagonal part, which we call E. And we don't need the small diagonal part. This is the decomposition. And we don't need to learn the big diagonal part because we know exactly what it is. This is exactly the matrix that would zero out the diagonal of R. And we had this nice hierarchy in terms of representation power because we saw that regular factorization machines are a special case of diagonal plus low rank with rank 1. As we increase rank, the representation power improves. And when we achieve full rank, it's equivalent to the original field-weighted factorization machine. Now let's see some results. So in terms of accuracy experiments, we tested on several data sets. In these slides, I'm going to present only one of those because, well, we have limited time. We did hyperparameter tuning, we tested several embedding dimensions, and we compared low rank to pruning in a fair way in terms of making sure they have the same number of parameters. So here is a chart for several charts for the Criteo dataset. Now you can see that for each dataset, the red curve, which is the diagonal plus low rank part, as the rank increases, the performance increases, and it always stays between two lines, the factorization machine and the field-weighted factorization machine. This essentially corroborates our claim of representation power that increases between factorization machines and field-weighted variants. And this happens for all our data sets, but, well, we don't have time to do it. We also measured latency in a production system. And what we did was we chose the rank that achieved a performance that is similar to the pruned variant in terms of offline testing. And then we tested the latency. So we can see there is a large improvement in scoring latency and a smaller improvement in ranking latency, essentially because ranking contains scoring, but, well, does many other things except scoring, like targeting and things like that. So to summarize, we have achieved the goals. We have fast inference. Context features are practically free. We show in the paper that we have a better speed and accuracy trade-off. And we show the nice hierarchy of models between factorization machines and field-weighted factorization machines. In the paper, we discuss more things, like why not just low rank, and why do we need a diagonal part? Why not approximate it after we finish training and train an approximation in the first place? And we show also inference speed experiments to corroborate our claim of a better trade-off between accuracy and speed. Thank you.
Thank you. Do we have any questions from the audience? Okay. I have a question online here. What's the typical Latin embedding dimension you use?
So here we used 8 and 16. This is what is typically used in papers. Some papers use 10, some papers use 20. In the production system, it's 12, but these are the embedding dimensions.
Okay, you have time for one more quick question? I have one just out of curiosity. You mentioned you focus on this particular variant of factorization machines. How hard do you think it would be to apply the same ideas to other variants?
So this idea, I believe, can be applied to higher order factorization machines. Then you need higher order tensor factorization of field interactions. But that's, well, the only idea I can think of right now.
Okay, thank you very much. Let's thank the speaker again.